In this chapter, we will be reviewing and introducing some ideas in statistics. In this lesson, we're going to introduce what we call the standard normal distribution.
Okay, everybody. So in a previous lesson, we looked at the normal distribution and gave a little bit of an introduction to it and how it works and how it can be used for some, or we at least gave an idea of how it might be used for some as a predictive tool, I should say. Now we're going to look at the standard normal curve. And now we're really going to be able to do stuff with this. So we want to go back and talk about the Z-score here. Okay, and remember that a Z-score is a form of ranking. Okay, a positive Z-score means you're above the mean, negative means you're below the mean. And the Z-score always refers to the number of standard deviations that you are away from the mean. Okay, and so a larger positive one means you're further away from the mean. A lower negative one means you're further away from the mean, but in the negative direction, in the low end direction there. It depends on the context whether that's a good thing or a bad thing. Okay, so Z-scores can be used to compare different normally distributed data sets by comparing their Z-scores. And so in a previous video, I did a little thing where I compared Al and Bob. They're two students from two different classes here. Looking at their marks on an exam, you really can't compare how they did to each other because the circumstances of their different classes have an impact on their mark. Really what you got to do is you got to look at how they do with respect to their group and then compare that to each other. And that's what we do here with the Z-score. We take a data item, compare it to its group, and then we compare those to each other here. So let's take a look first of all at this example here. It says Ashley's class wrote 3 diploma exams and the results are shown in the table below. Okay, so we've got the mean, we've got the standard deviation, and we've got Ashley's mark for each one of those. Now what we're going to do here is we're going to calculate the Z-score, or Ashley's Z-score, sorry, for each one of these classes here. Because we're going to see in which class she did the best. Now, it's not necessarily an issue of her mark, okay, because it's how she does in comparison to the rest of that class. That's what's important here. So let's take a quick look here. So her mark here, in this case, is 85. So it's her mark minus the mean, 64, over the standard deviation, 12 here. So I just got my calculator off to the side here. So 85 minus 64 divided by 12. And we see that she's got a Z-score in English of 1.75. So she's 1 3/4 standard deviations above the mean, which is really quite good. Okay. Let's take a look at her math mark here. Ooh, she got a 79 on the math mark here. So 79 minus the mean of 60 over a standard deviation of 8. So let's take a quick look at that. So 79 minus 60 divided by 8. Ooh, that is to the nearest hundredth here, 2.38 standard deviations. Okay, that's really good. And over here with social, she got 88. Minus 65 is the mean over the standard deviation of 16. So 88 minus 65 divided by 16. And we've got a standard deviation of a Z-score of 1.44. So even though she got the lowest mark in math, okay, when you compare the actual marks, compared to the group that she was in, okay, and when you compare how she did per group here, she did the best in that math class because she's 2.38 standard deviations above the mean in that class, and in the other classes she's not nearly that high up. Okay? So relative to the other students in the class, in which exam did she do the best? Well, we just said that was math 30-2. And that's really how you should be comparing that. Now you're going to find most of the time we don't. Okay? We just look at the mark that you get, and that's enough for most people, but it's really not the correct way to compare. Okay? So anyway, we can compare these Z-scores on a standardized normal distribution curve. So what we're saying here is that, look, if this is what's really important in terms of comparing people or comparing objects or whatever, then maybe what we should do is we should just write everything in terms of Z-scores, and that's how we'll compare them. We'll just use all of this information to just get the Z-scores here and kind of standardize everything. We'll just make everything Z-scores. So on a standard normal curve, the mean is going to be 0, and that's because the z-score of the mean is 0. Okay, and we talked about that in the previous lesson here. So we're going to compare Ashley's exams on the curve below here. So actually, we should ignore that. That 24 there is probably a little bit confusing. We want to get rid of that. If this is going to be a standardized normal curve here, then we're talking about z-scores down here. The z-score of the mean is 0. And then we've got over here, this would be 1, this would be 2, and then way over here is going to be 3. Here's our -1, -2, and then way over here is going to be our -3. Now, I know it's going to be written a little bit later on in this lesson, but it's probably worth mentioning right now that it's very rare to be either +3 or more or -3 or less here, standard deviations away from the mean. Okay? Most of the time, by the time you've gone out to -3 or +3, everything inside here, that is typically the vast majority of the data. So you don't typically talk about z-scores that are like 4 and 5. That's really, really quite rare. So here's where she's at. For her English mark put her at 1 3/4. So this was English 30-1. Math had her at 2.38, so she's out here. Math 30-2. And social 30-1 was 1.44, so that's a little bit less than halfway there. So this is social 30-1. And that's where they're at here. So you can see she did the best in math, and then the worst there in social. Now she still did quite good in social. Don't get me wrong here. To have a z-score of 1.44 is still pretty good. You can see, okay, that this is the part of the population that she did better than. Because remember, this is a ranking. So if this is where she's at, and we always want a high mark, then this is the part of the population that she did better in, and that's quite a bit. So that still went quite well. Okay, so now what we're going to take a look at some examples here. Sorry, my mistake. No, we're gonna look at some summary material here first of all. So here's the standardized normal curve here with the mean at 0, and then every time we go up a standard deviation, we're just going to call it 1, 2, 3, -1, -2, -3. So these are the number of standard deviations that we go away here. So it's a version of the normal distribution just using z-scores. The mean is 0. The standard deviation is now exactly 1. Okay, so whatever the standard deviation was, because we've reduced it now just to z-scores, this is going to be a single standard deviation away. 100% of the data is below the curve. Okay, makes sense. And 50% is above the mean, 50% is below the mean. So there's nothing new in that regard. And remember that the probability of being in a certain area here, like I said before, is the area under the curve. So what we're going to do now is I want you to start to understand how that creates probabilities here. And here we go. So here's the information that we've needed to get to you here. Take a look at how this works here. If you've got a z-score that's between -1 and 1, okay, then you're in a group of the population that contains a little over 68% of the population, okay? So, in fact, I've got to zoom in a little bit on that. So, to be within one standard deviation of the mean means that you're in a group of the population that covers 68% of the group, okay? 68% fall within one standard deviation of the mean. Now, if you open that up a little bit and you go from 2 standard deviations above to 2 standard deviations below, or vice versa there, you'll see that that covers 95.5% of the data. So just covering that up here, 95.5% of the data is held between these two lines here. And then finally, to go from -3 standard deviations below the mean, or I should just say 3 standard deviations below the mean to 3 standard deviations above the mean, that accounts for 99.7% of the data, which is what I was referring to before. It's very rare to have a z-score that's below -3 or above +3. Now, it does happen, but it's a very, very small probability that'll happen. Okay? So let's zoom out again. Whoops, zoom out again. So here we go. So some things to notice here. Over half the data is within one standard deviation of the mean. Yep, 68%. Almost 95% is within 2 standard deviations, and almost all of it is within 3, which is what we were getting at. Z-scores larger than 3 or smaller than -3 are very rare. Okay, really important point here. And I bring that up because sometimes I'll see people draw a normal distribution, and what they'll do is they'll just put all sorts of lines on it, and that indicates immediately that there's a little bit of a misunderstanding as to how that works. Okay, now you don't have to memorize these numbers. We can use your calculator to produce these percentages. These numbers here and a whole lot more are programmed into your calculator. Okay, so you just got to learn how to pull those numbers out. Or we can also use a Z-score table, and we'll pull that out in another lesson here, because you should know how that works as well. But to start off with here, let's take a quick look at how we're going to use the calculator to do this. So calculating probability, or the area under the curve here. Now, your calculator has got a feature on your calculator, got a feature called the normal CDF, or the normal cumulative distribution function. Cumulative meaning is that it adds up all the probabilities in a certain zone or certain area under the curve here. So to get to it, and I'll show you how we do that here. I'll put my calculator right here. We're going to press second, okay, and then we're going to press vars. Now that's probably a button you haven't seen all that much, but here's the vars button down here, and notice right above it, it's got the DISTR, distribution. So we're going to press vars, and that opens up this menu right here. What we want is number 2, the normal cumulative distribution function. So we press enter to choose that. Now, some of your calculators are going to do this a little bit differently. What my calculator is waiting for me to enter in here is a lower bound and an upper bound. Now, it might make more sense to think of it like this. What the calculator is going to do here, okay, we've got this normal curve. I want to know what the probability is of, let's say, being in this particular little region right here. It might make more sense to think of this as a left bound and a right bound, because that's where we're going, left and right here. So this is my lower bound, this is my upper bound, according to what the calculator is going to say here. But you might think of this as left and right instead. Okay, and so what I do is I tell the calculator what the left data value is, what the right data value is. I let it know the mean and the standard deviation. And when I press paste and then enter, okay, what it does is it takes all that information, shoves it into the normal distribution function, and it'll tell me what the probability is of being between those two data values. Okay, on your TI-83 calculator, you're basically going to write it all out. You're instead of having the calculator paste it in, you're going to put it in. And what you would do is you would use the comma button. You'd go the lower value, comma, upper value, comma, mean, comma, standard deviation. And just so that you know here, your comma button is this button just above the 7. Okay, that's a comma button. Now, just a few other things before we get into it and I start showing you some examples here. If you want the entire area below a data value, okay, in other words, if I don't know what the low bound is and I'm going to let it go forever, I'm going to enter a -10 to the 99. The calculator will understand that to be, oh, you mean like infinitely to the left. Now, I understand that if we're talking about exam marks, it doesn't make sense to talk about an exam mark that's less than 0. Don't worry about that. Because of the nature of this particular curve, if you don't put a low-end boundary on that, then it's going to have to be -10 to the 99. Same thing if there's no upper-end boundary. If there is no right boundary, then it's going to be 10 to the 99. We're going to let the calculator think it's infinite. Okay? When we're talking about Z-scores, and sorry, I should go back and say, it's because this is really just an approximation to reality, okay? So don't worry about trying to get all clever and like with marks thinking, well, the maximum mark you can get is 100. Okay, don't worry about that. We're not going to go there. Now, if you're using Z-scores, you're always going to use 0 for the mean and 1 for the standard deviation if we're talking about Z-scores. Okay, I say that again. If you're not using Z-scores, then you can just use the regular old mean and standard deviation that you're given, and that's fine. Now, that probably doesn't make a lot of sense. We got to show you what it looks like when you actually use it. Okay, so for our first question here, it says, let's test what we saw in the previous graph here. So we want to calculate the area within one standard deviation of the mean. Now, previously we saw that amounted to about 68% of the data. So let's just double check and see if that's actually what we're going to get. So we're going to go second vars to get into the distribution menu, normal CDF. And I'm going to let the low bound be -1, the upper bound be 1. Now, the calculator defaults to thinking that mean and standard deviation are 0 and 1, which is good. Okay, so I'm going to plug that in. So this is what this would look like. This is what you would do if it was in the a TI-83 calculator. -1, comma, 1, comma, 0, comma, 1. Press enter. And there it is. We get 0.6826. So 68.3, okay, 68.3% of the data is within one standard deviation of the mean. What would it be if it was 2 standard deviations of the mean? Well, I already know that should be about 95.5%, but let's just take a quick look. Okay, so second vars, normal distribution, -2, 2. I still like the 0 and the 1 there, so enter, enter, press enter for paste. And there we go, 0.954. Okay, so 0.954. Oh, and I probably did that wrong here. Well, it's okay. 68.3%. I've already converted that. And this should have been -2 to 0 and 1. We're getting 0.954, which is 95.4%. Okay. Good. Okay. So this question says, calculate the area below a Z-score of 0.36. So just slightly over here, this red line is at a Z-score of 0.36. We want to know what the area is under the curve behind that. Or what this is asking, probably better stated, is what's the probability that some data value has a Z-score less than 0.36? So to get this in, put this in the calculator, I will do normal CDF. I don't have a left bound. It goes forever to the left. So I'm going to enter -10 to the 99. But my right bound will be 0.36, assuming that I'm using just Z-scores. So my mean is 0, and my standard deviation is 1. Now let's plug this into the calculator. Oops, wrong button. Normal CDF. My low bound is -10 to the 99, so it's going to be -10 to the 10 to the exponent 99. Now there are other ways you can enter that in, but that's probably one of the easier ways of doing it. -10 to the 99. 0.36 is my right bound or my upper bound. I'm still using Z-scores. That's what it should look like. Okay, if you're using the TI-83, press enter. And I'm getting 0.64. Okay, 0.64 or 64%. Okay, there's a 64% chance or a 64% probability here that that's going to be less than 0.36. The area under the curve, if you're going to use units here, is 0.64. Okay, because all of the data under the curve, because all of the data shows up under the curve, 100% is under the curve. The total area under this curve would be 1. This is just 0.64. Okay, here the question says calculate the area above a Z-score of 1.34. Now 1.34 is going to be somewhere out here. Because remember, the mean is 0. So I'm looking for that area right there. So there is no upper bound. So to enter this into my calculator, this would be normal CDF. This time my low bound is positive 1.34, but there is no upper bound. So it'll be 10 to the 99. The mean is 0. The standard deviation is 1. Okay, and remember, when I say calculate the area above, area and probability are the same thing here. So I'm basically asking what is the probability of having a data value that's got a Z-score greater than 1.34. Okay, so now let's take, get in here, we'll grab that normal CDF. This time my low bound is 1.34. My high bound is positive 10 to the 99. Mean is 0, standard deviation is 1. Does that look the way I want it to? Yeah, 10 to the 99, press 0. Okay, and we get that that is going to be equal to 0.09. In other words, there's a 9% chance that a data value will have a z-score of greater than 1.34. And that actually makes a fair bit of sense. Okay, remember that by the time we get out to 2 standard deviations out, okay, there's 95% of the data is between -2 and +2, which means there's only like a little bit left over up here. Now, don't think of it as 5% left over. It's symmetrically distributed here. So there's 2.5% above 2 standard deviations and 2.5% here below -2 standard deviations. So actually, yeah, that 9%, that makes a lot of sense, that there would just be about 9% left over here. It drops off quite quickly. Okay, so in the previous questions, we were looking at using the normal CDF function, the cumulative distribution function, with z-scores, but it doesn't have to be z-scores. So remember this question: the mean number of hours an infants are sleeping is 13 hours. Okay, so we know the mean is 13, with a standard deviation of 2. Okay, and this is what that's going to look like. And now even notice here that I'm giving you a bit more on this graph than you really need here. But here we go. What percentage of infants sleep between 10 hours and 14 hours per day? Okay, between 10 and 14. Well, that means that our low bound here is going to be 10. Our high bound will be 14. This time I'm not going to put the mean and the standard deviation in terms of like as 0 and 1, because these are not z-scores. These are actual data values. So if I'm using the actual data here, then I'm going to use the actual mean and the actual standard deviation. But that's okay. The calculator has no problem with that. Okay, so remember that this feature here is finding the area under the curve of a normal curve, but here we want to treat this as a probability. Okay, what percentage of those infants there? So we're going to enter 10 as the low bound, or the left bound, 14 as the right bound, mean is 13, standard deviation is 2. Put that in, and we get 0.625, 0.625, which means that the number that we're looking for here is 62.5% of the infants that these nurses are looking after will sleep between 10 and 14 hours. Now, by the way, I don't want people overthinking this. When I say between 10 and 14 hours, I'm including the 10 and the 14. I'm not strictly speaking, between them, as in not including the 10 and not including the 14. Typically, when we mean that, we are going right to the 10, right to the 14. Just so that there's nobody overthinks that and puts in the wrong values when we're asking you to find probabilities here. Yeah, so like just to go back to this, you'll notice here, what percentage of infants sleep between 10 and 14 hours? I did not put 11 and 13 as my bounds. I didn't come in an hour from the low end and an hour from the high end to get the between there. Okay, we go from 10 to 14. What percentage of infants sleep above 15 hours? Okay, normal CDF. Whoops, CDF here. If it's above 15 hours, 15 is my low bound. If no high bound is given, then it's 10 to the 99. And again, 13 and 2. Okay, so here we go. Second, get in my distribution menu. 15 is the low bound. 10 to the 99 is the high bound. And 13 and 2. Nothing's changed there, so I'll just press enter and enter. Okay, good. That's what that should look like. And we get 15.9. So 0.159 or 15.9%. Almost 16% of the babies are going to sleep above 15 hours a day. Now, 500 infants were monitored for this study. How many infants sleep less than 12 hours per day? Okay, how many? I want you to think about that. How do you convert a probability, okay, into an actual number of people? Well, what you do is you multiply that percentage in decimal form by that value. Now, the nice thing is, the beautiful thing is, normal CDF, oh, and I wish that looked better. I'm going to fix that up here. But normal CDF spits out these values in decimal form. So I will take 500 and multiply this by the normal CDF. I did it again. I keep wanting to put the F there. I need to put the D. CDF Less than 12 hours. Well, no low bound is given, so I'm going to use negative 10 to the 99. Okay, my upper bound will be 12, and my mean is 13, and the standard deviation is 2. Now, here's a good example of what I was referring to before. It doesn't make sense to talk about babies sleeping a negative number of hours. I mean, the lowest they could possibly sleep is 0. But when we're using this function right here, don't overthink it like that. Just let this go. If there's no low bound given, we're going to let this be negative 10 to the 99, and we'll let the calculator deal with that little issue there. Okay, because it really, again, this is an approximation to reality, so I got to work within that approximation. So now, this will be 500. Okay, I'm going to pull out the normal CDF. There is no low bound given, so negative 10 to the 99. The high bound is 12. And again, the mean and the standard deviation are the same as before, so press enter. Okay, let's just double check that 500 showed up there, and it did. Okay, so 500 times the normal distribution. And that gets me 154.3. 154.3. What do you do? Do you round that up or do you round that down? Now, it turns out, for the most part, you can make an argument for both directions here, that you could either round that up or round that down, and that would be correct. And I believe in most situations, either one of those is acceptable. But I tell you what, let's just make a rule here. Let's round people up. Let's always just round people up. Okay? So 155 babies. And now finally here, how many infants sleep more than 12 hours per day? Okay, we're still assuming we've got 500 there, so this will be 500 times the normal. There, I did it right this time. CDF. More than 12 means 12 is the low end. 10 to the 99 is the high end. 13 and 2. This will go back to the calculator here, and again, this will be 500 multiplied by the normal CDF. This time 12 is the low bound. Okay, the high bound will be 10 to the 99. Sorry, I just had to double check there. It was 12 hours. 13 and 2. Paste that in there. Press enter. And we get 345.7. So 345.7. And just like we did before here, let's round that up. Okay. It doesn't matter which direction we go in those particular instances here. And again, I have sat through a little debate and watched it happen, and there are good arguments to go either way here, so it doesn't really matter. Let's just round that up with people. So 346. The life of a particular lawnmower engine is normally distributed with a mean of 8 years and a standard deviation of 2 years. Okay, so we've got this. The mean is 8 and the standard deviation is 2. So it's important to have that identified here. What is the probability? Okay, so I'm very likely going to use the normal CDF here to 4 decimal places, okay, that an engine lasts between 7 and 10 years. Okay, well, my mean here is 8, so 7 is going to be over here, and 10 is going to be over here. So I'm looking for the area under the curve from 7 to 10, okay? So this will be normal CDF, 7 to 10. And in this case, I know the actual mean and the standard deviation, so I don't need to use Z-scores. So go to my calculator, press second, vars, get into the distribution, normal CDF, and our low bound is 7, high bound is 10. This case, the mean is 8, but once again, the standard deviation is 2. Good, low, high, mean, standard deviation, good. And to 4 decimal places, that's 0.5328. Okay? So this is 0.5328, which basically means we're looking at 53.28% of those lawnmowers are going to last between 7 and 10 years. Now that's a pretty good thing for the manufacturer to know, to have an idea about the lifespan. Because now think about it. Why would a manufacturer be really curious about that kind of information? Well, because they're probably going to have to offer a warranty of some kind. And so this gives them the way of understanding what that warranty should look like, so they don't spend a lot of money on that. What is the probability to 4 decimal places that an engine lasts more than 10 years? Okay, so again, I'm asking for the probability. So that's a normal CDF. More than 10 years means 10 is my low bound. Since no high bound is given, it's 10 to the 99, and the mean is 8. The standard deviation is 2. Okay, so here we go. Let's go back into that. So back in my distribution, normal CDF. This time my low bound is 10. My high bound is 10 to the 99 because 1 isn't given. Same question though. So my mean and my standard deviation are both 8 and 2. Nothing's changed. Paste. Yeah, that looks the way it should. Press enter. And I get 0.1587. Whoops. That's right. 0.1587 or 15.87%, okay, are going to last longer than 10 years. Now down here, 90% of the engines will last less than how many years? Okay, so here I'm giving you the probability and I'm asking you, okay, how many years will 90% of the engines last less than? So what's that upper bound that makes that work? Now, I could start guessing at that, but that's going to take me a while to kind of figure that out here. Like up here, I know that 15.87% last more than 10 years. So if I'm looking for what's the largest lifespan for 90% of the engines, well, then I know that that's got to be a little bit more than 10 years. I just don't know exactly what that's supposed to be. So if given the probability, we need to calculate the data value. And in order to do that, we need the opposite or the inverse function of normal CDF. And that's what we're going to look at next. What tool can we do we have at our disposal to go backwards? Normal CDF takes data and produces probabilities. Well, what happens if I have a probability? Okay, so what do we do when we're given a probability and want to create a data value? Now this is a little bit more tricky, okay, because previous to this, think about the way that worked here with normal CDF. I would give it like a low bound and a high bound, and it would give me a number, a probability of being in between here. Well, it's not quite straightforward to give a to put in a probability and have the calculator give you a low bound and a high bound, because really that's pretty fluid. I mean, 50% of the data could be from the middle to all the way to the left, middle all the way to the right. I could pick a kind of a part way in between where there's 50% of the data in there. Like there's no one answer to where is 50% of the data. So to kind of get around that and to make it so that there's one way of interpreting this, what we do here is we use the inverse norm function on the calculator. And if you go to your distribution menu, so second vars to get into distribution, you'll see it's right below the normal CDF. There's the inverse norm. Now, what it does is it takes an upper boundary and gives you, it gives you the upper boundary when you give it the total area to the left, okay, in a distribution. So we are always going to be plugging this in. Okay, so we plug in this probability that goes all the way from here to the left, and then the calculator will spit out that data value right there. Okay, and it's always it is always once we've given it the data to the left. Okay, I hope that makes sense here. It's not the data value in between. It's starting from way out here to negative infinity. We're assuming that the probability that we're entering in, or the area we're entering in, is all the way to the left to this point, and the calculator will tell us where that occurs. Now, how you do that is you go back in your vars menu, select number 3, then you're going to enter the area into the left as a percentage. Okay, so not as a percentage, as a decimal. This is what I meant to say there. Then you're going to tell it the mean and the standard deviation. Select paste here, and then enter. Or if you're using a TI-83, area to the left, comma, mean, comma, standard deviation. So just be aware of how that looks there. Just a couple other things before we go on and start working with questions here. Remember that the total area under the curve is 1. because this covers 100% of all possible results in this particular analysis here. If you're given the area to the right of a data value, so if I give you, okay, so if I tell you that out here, for example, you know that what this area is, okay, to get this area right here is going to be 1, or I should do it, I'm sorry, I'll do it the other way. Yoink. This area right here will be 1 minus that area, because the total area under the curve should be 1. Okay, so whatever this, so if you know that this is 10%, then I know that this over here is 90%. And that, remember that the data is symmetric about the mean, so you've got 50% below the mean, 50% above the mean. Okay, let's take a look at some questions here, and I hope it makes sense, because between the two of them, the inverse norm tends to be the slightly more conceptually difficult tool. Okay, so for this first set of questions is really just about using the calculator here. So for each of the following standard normal distribution curves, okay, which means, by the way, that as soon as I say standard normal distribution, which means I'm using Z-scores, so my mean is 0 and my standard deviation is going to be 1. Okay, so that's going to be true for all of these things here. We want to find the Z-score. Now, just some clarification as to what this is saying here. I want to know what this Z-score is right here. This is saying that the probability that the Z-score is less than, we're saying that the Z-scores are all, this is poorly, a little bit poorly worded. The Z-score that we're looking in here, if you take the probability of that Z-score, the probability of the data being less than that is going to be 0.9147. Okay, so this area right here is 0.9147. If you know that's true, then what we do is we go to our inverse norm and we type in 0.9147. That is the area to the left of that Z-score. The mean is 0, the standard deviation is 1. That's true. That's what it should look like. And so what that means is that particular Z-score there is going to be 1.3, what do they want it to? Nearest hundredth, 1.37. Okay, so this Z-score right here is 1.37. The probability that a Z-score is to the left of that is 0.9147. Let's take a look at a few more here. Whoops. So here, I'm looking for this particular Z-score here, the area, okay, to the left of it, or the probability that a Z-score is to the left of that is 0.0125. So up here in the calculator, I'm going to put in 0.0125. The mean is going to be 0. The standard deviation is going to be 1. So I plug that into my calculator. Inverse norm, 0.0125. The mean is 0. Standard deviation is 1. Paste that in there. And in this case, we get that the Z-score is negative 2.24. Now, that communicates to me that this should be to the left of the mean quite a bit. And actually, that's what I am seeing here. This is quite a ways over. So, yep, that's consistent with what I have drawn out here. Here, I'm telling you that the probability, okay, that a value has a Z-score greater than Z2 here is 0.6628. So this right here is 0.6628. That is not what I need. That is not what I need to enter in here. In the inverse norm, what I need is the area to the left here. So I need this area. That's okay though, because it's going to be 1 minus 0.6628. It's just the exact opposite of that. So I just subtract this from 1. And then my mean is still 0 and my standard deviation is 1. So go to my distribution menu, grab the inverse norm. This is going to be 1 minus 0.6628. And the nice thing is you can actually write that expression, and the calculator will do that for you. Whoops, I don't know why I deleted that. 1 minus 0.6628, sorry, down 1. The mean is still 0, the standard deviation is 1. And I'm getting negative 0.4201. Or to the nearest hundredth, I believe, is what they've been asking for, just negative 0.42. And actually, that makes sense. If you take a look at the diagram here, yep, where that boundary line is to the left of the mean by a little less than halfway. So it's good. Now, this one is a little bit different here because the area that I'm giving you here is the area between these two, between the mean and that particular z-score. Well, I want the full area here. But I just got to remember that this is half. Okay, this is half of the full graph here. So which means this is 50% of the data here. So to get all of the data up to that z-score, I just got to add those two together. So this is going to be the inverse norm of half the data plus this 0.3944% of the data, 39.44% of the data. The mean is still 0, the standard deviation is 1. So grab my inverse norm, 0.5 plus 0.3944. Standard deviation, sorry, the mean is still 0, standard deviation is 1. Paste that in. And we're getting a z-score of 1.25. And again, that makes sense, okay? That makes a lot of sense here because 39.44%, that pushes us quite a ways above the mean there. Another way of asking this question here would be to determine the two z-scores indicated on the diagram. Now, you really got to understand what's going on here for this to make sense. I can only do this one at a time. So let's do Z1 first. To get Z1, I'm going to use the inverse norm. And I know that my mean and my standard deviation are going to be 0 and 1. I get that. But what I need is this area to the left of that value here. It would help for me to recognize that this line down the middle is the mean. Well, okay, I don't really care what's going on above the mean. That's not very helpful here. But remember that all of the data less than the mean, that's 50%. That's 50%. So all of this is, okay, this is all half of the data. If I subtract this little bit that's between Z1 and the mean, then what I'll be left with is all the data that's less than the mean. Or sorry, not less than the mean, less than Z1, which is what I want. Okay, I want just this little bit of data here that's less than the Z1, the z-score right there. So that's how I'm going to do it. Half of the data minus this bit right here gives me the value that I'm looking for. So now on my calculator, I'll clean this up a little bit. Second distribution, inverse norm, 0.5 minus 0.1137. Again, the mean and the standard deviation, nothing has changed there. And I get that the z-score here is negative 0.29. Okay, now let's turn our attention to Z2. Again, I'm going to use the inverse norm here. But this time I want all of the data to the left of that z-score. Well, I know that this is, what is that, 25.14% to the mean. See, but now I got to remember that this is now 50% of the data. So I've got, think of it like this. I've got 50% of the data plus this bit right here. So all of the data to the left, or all of the area or probability to the left there is going to be 0.5 plus 0.2514 and a mean of 0 and a standard deviation of 1. That's going to give me everything up to that point. So it really helps to do these separately, do them individually here, so that you don't start mixing up these two numbers here. Just look at what it is you're trying to get, and look at how it's being related to the mean. So this is 0.5 plus 0.2514. Mean is 0, standard deviation is 1. Paste that in, and we get that that's going to be 0.68 when I round it. There's the z-score that we're looking for. Okay, now we have a tool to go back and answer one of those previous questions here. The life of a particular lawnmower engine is normally distributed with a mean of 8 years and a standard deviation of 2 years. 90% of the engines will last less than how many years? So here's my data value. I know that this right here, I want this to be 90%. And I want to know where this is here. Now, because I've got the actual mean and the actual standard deviation, the calculator can actually give me the actual lifespan of this, not just in terms of a Z-score. So my time here, this x right here, this lifespan, will be the inverse norm of 90%, but this time the mean is 8, the standard deviation is 2. Oops. So on my calculator, inverse norm, I'm going to clear that out here, 0.9. But this time the mean is 8, standard deviation is 2. That's what that should look like. And what this means here is that 90% of these engines will last less than 10.6 years. Okay? Roughly. Now, I'm not being asked to do any kind of weird rounding. So I'm just going to round to the nearest whole at this point here. I'm not being asked to come up with like a warranty, which might change the way I round this a little bit. So I hope that makes sense here. The issue here for this question is really that I can use the actual mean and standard deviation to get an actual lifespan. Okay, so here we go. The marks on a test are normally distributed with a mean of 75. Okay, here we go. The mean is 75, and the standard deviation is 11. Kim's score is in the 83rd percentile, which means 83% of the class scored below Kim. So that's a really nice statistical tool that runs in conjunction with this inverse norm feature. Because anytime you talk about a percentile, you're giving the percentage of the population below whatever data value you're looking at. So Kim's score here, we know, okay, so here's the class, the mean is 75, the standard deviation is 11, and Kim, here's Kim's mark. 83% of the class scores less than her. That's what that means. So to get her mark, this is Kim's mark here, this is going to be the inverse norm. And it's beautiful that working with a percentile is wonderful because you can just plug that in. The inverse norm is quite honestly expecting the percentile right there. So this is a great overlap between these two ideas. So inverse norm, 0.83, 75 and 11. Good, that's what it should look like. And so she got, okay, to the nearest 10th, 85.5%. Okay. Now, what would Kim have had to score to be in the top 5% of the class? Okay, so now we're asking the same thing. 75, standard deviation is 11, but we want to know where would she have to be, where would her mark have to be so that she's in the top 5%, which means this bit right here is 5%, but that's not the part that I need. I need the part below her. If she's in the top 5%, that means she is in the 95th percentile. Okay, that 95% of the data is below her. So now I can use that here. We'll figure out what her mark would have to be. Inverse norm, okay, 0.95. This mean was 75. The standard deviation was 11. So here we go. Inverse norm, 0.95 this time. 75 and 11. That's not going to change. And so she would have had to have gotten at least, what was that, 93.1%, rounded to the nearest tenth. Okay? So I hope that gives you some idea of how these two tools in the calculator work, this normal CDF and the inverse norm feature both work.